Hi, welcome you again to the stress lecture series. So in this lecture, I'm going to discuss all about the hydrostatic and deviatoric stresses. So two types of stresses are here: hydrostatic, hydrostatic, and deviatoric stresses. Deviatoric, deviatoric stresses. So these two types of stresses are here. So these two are subsets of any given stress tensor, which, when added together, give the original stress tensor back, and the hydrostatic stress is related to the volume change, and while the deviatoric stress is related to the shape change. So, so any stress tensor can also be decomposed into hydrostatic stress plus its deviatoric stress. So, similarly, a symmetric tensor, any tensor can be divided as symmetric as well as antisymmetric. Similarly, this tensor can also be decomposed into hydrostatic and the deviatoric stresses. So this hydrostatic stress tensor is stress is related to the volume change, related to the volume change, change, volume change, and the deviatoric stress is related to the shape change, shape change. So hydrostatic tensor. So say for example here, it is a glass of water or something like that. It's a glass of water, or it may be river. So if you swim or if you sink beneath the water, if you are here, then the pressure exerted by the water around you is called hydrostatic pressure, because the force around you from the water is equal and same. Say for example here is the body. If you apply force here, if you apply force here, if you apply force here, and if all the forces say here 1 2 3 4, if all the forces around this body is equal or same, then it is called hydrostatic forces. All the hydrostatic stress or something. And shear stress, if there is no any if the forces are not equal to each other, then the stress is called the deviatoric stress. So what is hydrostatic stress? Hydrostatic stress is simply the average of the three normal stress components of any stress tensor. Say for example, this is stress tensor T. T is a stress tensor, say here, and its components are sigma 1 1, sigma 1 2, sigma 1 3, or sigma xx, sigma xy, sigma x. This doesn't matter at all. So, or if you want, then you can write, yeah, because our previous terms are similarly like that. So, so the hydrostatic status is sigma xx, sigma xy, sigma um, xz. Say these are any tensors, not hydrostatic tensor. Yep. Yx, sigma yy, sigma yz, and it is sigma zx, sigma zy, and sigma zz, right? So from the definition of hydrostatic stress, we know the average of the three normal stress components of any stress tensor. Average. What are the normal components here? So average of three normal components, right? So here the normal components are here: xx, yy, and zz. Then the hydrostatic stress we can write down sigma A's or sigma hydrostatic stress or TA's, however you do it, doesn't matter at all. So you can write down sigma xx plus sigma yy plus sorry sigma and sigma zz divided by 3. So we can write down here 1 by 3 sigma xx plus sigma yy plus sigma zz. So from the summation convention, we can write down here sigma ii or sigma kk, doesn't matter at all. Sigma ii, say, or sigma kk, sigma kk, or something like that. So So there are many alternative ways to write down the hydrostatic stress or something like that. So from the definition of stress, we know the sigma kk or sigma ii is the trace of any tensor, right? Trace of any tensor is the summation of its diagonal components. So we can write down is also hydrostatic stress is nothing, but we can also 1 by 3 and trace of any stress tensor, right? Or we can write down here 1 by 3 sigma kk. It is also the first invariant of this of any stress tensor or something. So we can also the first invariant first we know from the if you have already taken if you have already watched the our my previous lectures tensor lecture series, then you say the first invariant is also the summation of the diagonal components. So we can write also the first invariant is if the first invariant is I1, then we can also write this 1 by 3 then I1, because I1 is also the same as this, then the trace of any tensor is same as this, something like this. Yeah. So it is a scalar quantity, right? So only the summation, we only sum the magnitude of the normal component, something, nothing else, and then divide these three. That means simply average. So it's scalar quantity. So it's regularly used if we write down it as tensor components. Then we can in tensor components we can write down here sigma hydrostatic stress is nothing but sigma hydrostatic stress 0 0 0 sigma hydrostatic stress 0 0 0, and often is written as in tensor component, something like that. Yes. Say for example, here we have a I'm going to give you an example of that. Say here so in tensor form it is written as something like that, right? Yes. So I'm going to delete this. So we have a say we have a distance or something of any point sigma equal to 50 30 20. Say here is 30 minus 20 minus 10, and it's 20 minus 10. Say these or one of this distance. So then what is the hydrostatic stress? Then hydrostatic stress is T or sigma hydrostatic stress is 50, this component plus this component plus this component and divided by 3. So plus minus 20 plus 10, right? Divided by 3, and it is equal to 13.3. So in tensor form we can write down here sigma is equal to 13.300 13.300 and 13.3. So in tensor form we can write down this hydrostatic stress. So in geodynamics and or any mechanical engineering, hydrostatic stress is huge significant or something like that. Okay, so if we transfer or if we transfer this hydrostatic stress, does it change? No, it doesn't change. So it remains the same. So so hydrostatic is if it's the hydrostatic stress, uh, then if we transfer this any something like that, then it doesn't change at all. It means that no shear stresses even arise. So every direction, principal direction with the hydrostatic stress, something like that. Yeah. So hydrostatic stress, and there is a relationship between the hydrostatic stress and pressure in science. Yeah, yeah. So pressure and hydrostatic stress. Hydrostatic stress. So what is the relation between the pressure and hydrostatic stress? Pressure is nothing but simply the negative of hydrostatic stress. That means if pressure is denoted by P, then is simply the negative of hydrostatic stress. That means we can write down here sigma 1 1 plus sigma 2 2 plus sigma 3 3 divided by 3, and it's negative. It's nothing. So the pressure tensor, the stress tensor containing P, say so then we can hydrostatic stress tensor can be expressed as something like that. So P hydrostatic stress is simply nothing minus P 0 0 0 minus P 0 0 0 and minus P. So hydrostatic can be expressed. Hydrostatic stress can also be something like that. Yeah. This is almost non-topic because hydrostatic stress usually have no impact on incompressible material at all. Yeah. So there is very little to discuss all about that. So I will concentrate. I will not concentrate on this issue at this moment like that. Okay. Now we can go the deviatoric stress. So what is deviatoric stress? Yeah, what is deviatoric stress? Uh, so at the beginning, I've already said that deviatoric stress is related to the shape change. So deviatoric stress is what's left after subtracting out the hydrostatic stress. The deviatoric stress will be represented by sigma prime. Say uh, if any stress tensor is denoted by sigma, then its deviatoric stress is sigma prime, and its hydrostatic stress is HYD or H or something like that. So its deviatoric stress is nothing. So its deviatoric stress is the simply remaining part of any tensor after subtracting the hydrostatic part. So sigma minus sigma hydrostatic part, right? Yeah, so it's nothing. So it's the hydrostatic part something. In tensor notation, it can be written as say sigma ij deviatoric stress. So ij minus. So what do we know from this? So we know that. So ij components, yeah, the Kronecker delta and sigma kk. So we know this, right? Or in pressure we can write down sigma ij plus pressure is something like that. So minus 1/3 and sigma kk is one third sigma hydrostatic stress, and hydrostatic stress is equal to the negative of pressure. So pressure is P and Kronecker delta Ij, something like that, right? So these are deviatoric stress. Deviatoric stress is related to the shape change. So for example, I'm going to give you an example. Say we have an example. We have this previous stress tensor. Say here we gave 50, 30, 20, 30, minus 20, minus 10, 20, minus 10, and 10. So hydrostatic tensor of this, we have already calculated that sigma is YD is 13.3. That means 50 minus 20 plus 10 divided by 3, right? So it can be written as so hydrostatic stress. So this tensor can be written as 13.3 0 0 0 13.3 0 and 0 0 and 13.3. So this is the hydrostatic stress tensor, right? Yeah. So we can express the deviatoric stress something. Um, so deviatoric stress is sigma minus sigma KCYD. That means we can return 50, 30, 20, 30 minus 20 minus 10 and 20 minus 10 and 10. This tensor minus this is the hydrostatic tensor. Yeah. 13.3 0 0 0 13.3 0 0 0 13.3, and the result is and that's our result is here third oops 36.7 The remaining part is the same, 0, 20. Here it should be 30 minus 33.3 minus 10.0. Here the remaining part should be the same. Yeah. It's 20 minus 10. So, yeah, so it should be the minus 3.3, because if we subtract 10 minus 13.3, then the remaining part is 3.3 here, right? If we subtract minus 20 minus 13.3, then it will leave us minus 33.3. Then 50 minus 13.3, then it will leave us 36.7. So this is the deviatoric stress of at any point. So if we add this, say, then if we add this sigma hydrostatic stress plus sigma, then it will leave us the original stress tensor. Say if we add this part and this part, this add this add this, then it will leave us the original part of it. So this is the hydrostatic stress. So these are the hydrostatic and deviatoric stress. There are many applications of this hydrostatic and deviatoric stress. So I hope you have enjoyed this lecture, and in the next lecture I'm going to see you all. Thank you.